Yeah, I guess we shall start. We have Isaac, our own PhD student, to talk about WCFS queues and a new analysis framework for various types of queuing models. Sorry. Yeah, go ahead.
Thanks, Praneeth. Yeah, and thanks everybody for coming to my talk. So before I get into the content, I just want to say that despite the fact that this is over Zoom, I'd love for this to be interactive. So if you want to unmute and ask me a question, I'd love that. If you put something in the chat, I can't promise I'll see it. So maybe somebody tell me, that would be great. Yeah, so I'm going to be telling you about these type of queues called WCFS queues, which we came up with. And I'm excited to tell you about this. This is research with my advisor, Mark Walter, who's here in the meeting, and Alan Charles Wolf, who's another professor here at CMU. So let me tell you sort of how I came to this line of research, these sort of ideas. I was looking at a bunch of queuing systems, and we found this unexpected similarity. So I'm just going to briefly touch on a bunch of queuing systems, and they've got these weird things in common. So first, there's a queuing system called the heterogeneous MGK. And basically it just means there's a bunch of different servers, they all run at different speeds, and they're all working on their different jobs at their different speeds. And the queuing time in this system, it's an open problem. People don't know how to analyze this system. It's too complicated, it's too crazy. I'll tell you more about this system later on in the talk. Another system was this limited processor sharing system. So processor sharing is sort of an idealized version of what might happen in a CPU. You time share between a bunch of different jobs. And limited processor sharing is like that, but to reduce overhead, you cap the amount of sharing at some number of jobs. And again, response time behavior, analyzing the system, way too complicated. It was another open problem. But there were some similarities in terms of the response time behavior of these systems. And so, that got us thinking. We found more systems. A system called the threshold parallelism system, where different jobs each say, well, I can use up to this many servers effectively. So parallelize me across up to this many servers. So maybe this job we're giving 4 servers. This job we can go up to 2. This one, it can take up to 4, but there's only 2 left, so we'll just put it on 2 servers. And again, the response time behavior was an open problem, but it was looking really similar to the behavior in these other systems. So we were, what's going on here? And another system was called this multi-server job system. And in this system, every job tells you exactly how many servers it needs. And you have to give it just that many, or it won't even be able to run at all. And no existing policy was known how to analyze it at all. But we came up with this new policy, and it was fitting in the same category as all these other systems. It was called the ServerFilling policy. And so we've got this strange similarity of response time behavior of all these different systems, none of which anybody knows how to analyze. So we said, there has to be something in common behind all of these systems. And we discovered what all these systems have in common. And that's what I'm going to walk you through over the course of this talk. And we use that common behavior, that hidden shared idea, to tightly characterize the response time behavior, tightly analyze all of these different systems. And so they went from all being open problems to all being at least somewhat well understood in one fell swoop. Okay, so I used a lot of terms you might not know. That's okay. I'm going to be defining everything in a lot of detail. So as a warm-up, let me tell you about a pretty simple queuing system called the MG1. So here we have one server. We've got a queue. Jobs show up in the queue. Every job has a size. That's the amount of time it's going to take to run, which is distributed IID from some general job size distribution. So I'm interested in working in a stochastic queuing model where jobs have random sizes, arrival times are random, and this turns out to model how things behave in the real world pretty well. So that's why we've chosen this system. So we've got this general job size distribution. And jobs arrive according to a Poisson process. So if you're not familiar with that, just think it's memoryless. There's the same arrival rate at every moment in time, and we call that arrival rate length. And one pretty important quality of a queuing system like this is its load. The load is the fraction of the time the server is busy. So we've got jobs arriving lambda times a second, and they each need the mean job size worth of time on the server. So the fraction of time the server is going to be busy is this rho, lambda times E of S, and that better be less than 1, or else we'll never get all the jobs done. So, okay. What are we interested in measuring about these systems? We're interested in their response time behavior, and we denote that as a random variable with this letter T. And that's the time from when jobs show up to when they complete, thought of as a distribution. Okay, so an MG1, it's very simple. It's also very well understood. We know exactly how its response time behavior depends on lambda and S. So let me show you how that works. Here I've got a plot. On the horizontal axis, I've got the load rho, and on the vertical axis, I've got mean response time. And this will be for a job size distribution that's a certain hyper-exponential distribution I've chosen. And so here's what it turns out the mean response time is. And this is just a formula I can calculate explicitly. Now, as you can see, it's shooting off to infinity as load approaches 1. And that makes sense. As load goes to 1, our system's getting increasingly backed up. It takes longer and longer to finish the jobs. And so mean response time is going to infinity. To keep everything on one plot, it's handy to rescale mean response time by multiplying it by a factor of 1 minus rho. And when you do that, the mean response time under the scaled mean response time under an MG1 is just this straight line. And we actually know exactly what point it converges to as rho goes to 1. It's this quantity, the mean of job size squared divided by 2 E of S. And that tells us the heavy traffic behavior of this MG1. So we know exactly what it does at all loads, and in particular, under very heavy load. Okay, so this is an MG1. Any questions about this system? Okay, so now we're going to be moving on to something a little more complicated. Let's look at the MGK. So the K means that we have K different servers. And we're going to think of them all as running at speed 1 over K. So we're going from having one really fast system to maybe K different cores or K different machines in our cluster. And for this system, if we want to look at the same scaled mean response time, well, now we have to start simulating because we don't have any nice mathematical formula for things anymore. And when you simulate it for the same job size distribution as before, one gets this mean response time behavior. And notice it is converging to the same limit as rho goes to 1 that the MG1 converged to. And this has actually been proven thanks to this paper by Kollerstrom back in 1984. But it's really just this point at rho equals 1 where we really know what's going on with certainty. At all other loads, well, then we got to simulate. There are some bounds, but they're not great bounds. Okay, so that's an MGK, and we're just going to get more complicated. We're just going to go further into the territory of unknown from here. So next, let's take a look at the heterogeneous MGK. This was one of those 4 systems I showed on the first slide. So in this system, instead of all the servers running at the same speed, they've all got their own speed. So V1, V2, V3, etc. Okay, so again, we have to simulate because if we didn't know how things were working when it was all the same speed, we certainly don't know what's going on here from a mathematical perspective. And it turns out, lo and behold, we do the simulations, and it happens to converge to exactly the same limit, exactly the same behavior as load goes to 1. So this is that commonality I'm talking about that was so unexpected. They're all converging to the same point. It could have gone anywhere, but it decided to go to the same point. And do we know if that's always going to happen for all systems? No, it's an open problem. Or at least it was an open problem until this line of research that I'm going to tell you about today. So that's a heterogeneous MGK. Let's talk about another system. This was one called the limited processor sharing system. So the idea here, as I mentioned earlier, is it's inspired by a policy called processor sharing. Processor sharing is you split the capacity of the system equally between every single job in the system. So you timeshare among all of them. Now, that's a nice model of what happens in computer architecture a lot of the time, but it's pretty common that when you have enough jobs in the system, if you try to share among all of them, you get awful behavior. You get thrashing where you're moving there's tons of overhead. It's a big problem. So it's common to limit the number of jobs you're okay with running at a time, the number of threads you can have active, to some multi-programming level K. And we'll just take the K jobs that have been in the system the longest and share between those if we have at least K jobs. And, let's go and simulate it. We don't know how it's going to behave. Lo and behold, converges to the same point. What's its behavior? Again, open problem. But I want to stress something. It's not just that every queuing system converges to the same point. For contrast, let me show you the unlimited, the normal processor sharing policy. Its mean response time behavior is actually exactly known from a mathematical perspective, and its mean response time times 1 minus rho is just always the mean job size. In particular, it converges to a different limit over here. It converges to E of S. And in this picture, those values are kind of similar, but there are other job size distributions that definitely show up in reality where the gap between these two might be enormous. It might be a factor of 100. So finding all these policies that are converging to the same point is really something of a surprise. Okay, so that's limited processor sharing. Let's keep going. What about the threshold parallelism policy system? So here, as I mentioned, each job tells you, well, I can use up to 2 servers effectively. I can use up to 4, etc. And they can be parallelized perfectly across the number of servers that they can use, but no more than that. So we're going to be looking at the first come, first serve policy for this system. So what that means is when a job completes, the next job will move up. The next job, now it can use all 4 servers that it wants. We'll plop the next job into service. And this one, there's only 1 server left, so we'll squish it in there. Okay, so in this system, we got to simulate it. We don't know how it's going to behave, all sorts of possibilities. Maybe it's not as much of a surprise anymore, but it does converge to exactly the same point as mean response time goes to 1. This is getting increasingly surprising because these are really different systems. And so, it's getting increasingly unexpected they keep having the same behavior. Do we know they're going to have the same behavior? Of course not. It's an open problem. And again, if we'd done a different policy, we'd be converging to a different point. So say we had prioritized jobs that require that can use the most servers. We do the most parallel jobs first. Well, then our mean response time would go like this. If we prioritize the ones that needed few servers, it would go like this. So it's not like this is a foregone conclusion that they'll converge to this point. It only happens for some specific policies. Okay, let's talk about the final model, the multi-server job model. So this is something you see in data centers. Jobs will just show up and the user will tell you, my job needs to be parallelized on 15 servers. My job needs to be parallelized on 1,000 servers. My job needs 2 servers, etc. And you better give them exactly that number because it can't run without exactly the resources it specifies. So in this system, for all existing policies, all decisions of which jobs do you serve at what time, the behavior was an open problem. And in fact, they were all going to all sorts of different limits, and many were even unstable. Let me show you what that looks like. So here we've got our plot again, and if we take the first come, first serve policy for the multi-server job system, that means when a job finishes, just put them in arrival order. And if something doesn't fit, well, oh well, it doesn't fit. That system, it's even when we scale its mean response time by 1 minus rho, it actually runs off to infinity well before load gets to 1. So there's some threshold where above that threshold, it's just unstable. Jobs keep piling up forever. So that's certainly not, the same behavior that all these other policies have. And we thought about it for a while, and we came up with a new policy that's in this same group with the limited processor sharing, with heterogeneous MGK. And it's a policy called ServerFilling, and I'll explain it to you later in the talk. And it's got this exact same behavior. So as rho goes to 1, it converges right to the same limit of scaled mean response time at ES squared over 2 E of S. Okay, so we've got all these different policies. We know what's similar about them. Now let me tell you what we proved, not just what we observed. So here we've got our plot, and we prove a theorem. For all models pi in this special group of models, the special class of models called WCFS, which I'll define in a moment, subject to this minor condition on the job size distribution, the limit as load goes to 1 of the mean response time times 1 minus rho is this exact limit, ES squared over 2 E of S. That's pretty exciting. Previously I said we only observed this by simulation. Now we know it for a certainty. But actually, so that tells us exactly what the behavior is right here at load equals 1. And that's pretty exciting. But actually, we prove an even stronger theorem. So we look at the mean response time under one of these policies minus the mean response time under the MG1, which, as I said, is understood at all loads exactly. And we prove at all loads, this difference is in this small interval between two constants. And those constants are dependent on the policy pi, but importantly, they are not dependent on the load rho. So this is an additively tight bound on mean response time at all loads. So that's pretty exciting. And that's our main theorem of this work. Okay, so I want to pause here for a moment and see if there's any questions about, what I've talked about so far.
So Isaac, as stated, the first theorem doesn't follow from the second one. You are implicitly assuming that CL, CH are converging to 1.
So CL and CH are constants, not depending on rho. So if we multiply through this equation by 1 minus rho, then we'll have that this difference is something that is going to 0 because it's a constant times 1.
Got it. Sorry, I was being silly.
No problem. Thanks for the question. Okay, so we've got these theorems. So what I'd like to do now is I'd like to define this WCFS class of models, and then I'm going to walk you through an outline of how we go about proving this result.
Hey, Isaac, one more question.
Yeah,
so
please.
Do you know if the constants CL, CH you're giving are kind of tight in some sense?
So we looked into making them tight, and if you want to make them tight, you really have to get into the details of every single policy. So since our theorem is really about this whole class, WCFS, we know it's not very tight. So there's a lot of room for improvement there. And then you have to get into, for this policy, how tight can it be? For this model, how tight can it be? That's it. Well, thanks, Anupam. Okay.
Sorry,
yeah,
related to that. So then that includes, so that tightness concern is true even though the constants depend on the policy?
Well, okay, when I say the constants depend on the policy, really the only thing about the policy that these depend on, at least for our paper, are things like what's the K in MGK and things like that. They're not really using the tighter details of the policy, at least in this version of the theorem.
Okay, so basically they sort of intuitively you could say they depend on like the systems. I won't speculate. I'm curious to see.
Sure, and that's something that is in the paper, and I can show you that in more detail later. Okay, so to define this WCFS class of policies, first, let me give you a sort of abstract view of a queuing model. So here, we've got a bunch of jobs, and some of them are partially worked on. So they've got partial, we've done some work, but they're not totally complete. We'll call that amount of work we've done on them so far their age. And we think of a service policy as just picking out a bunch of jobs and saying, you know, you get this service rate, you get this service rate, you get this service rate. And that service rate is just the rate that that we're completing work on each of these jobs. It's the rate that the age is increasing. So boop, the age goes up on all these jobs we're working on. And we think of the size as being the point that age has to reach in order for the job to complete. So the job will complete when the age reaches the size, or in other words, the size is the amount of work you have to do in order to complete the job. And so maybe this job completes, and the service policy might decide to work on this job instead, now that it's got some free capacity. And our convention is to normalize the maximum service rate of the system to 1. So you see, at this moment in time, the service policy is giving out 1 total service rate. Okay, so that's a generic view. Now let's get into the specific qualities that generate this behavior that I'm interested in. So let's talk about finite skip models. So here we've got the same picture of the system, but now there's this region over here which we call the front. And it's got a limited finite size by some parameter n. And the rule is that the service policy is only allowed to serve the jobs that are in the front. So to be a finite skip policy, you must only serve jobs among the n oldest jobs in arrival order. And n has to be constant. You can't vary it with load or the system condition or anything like that. So that's a finite skip policy. Now, with that definition in mind, we can define a concept called a work conserving model. And this is going to be specific for finite skip policies. So in a work conserving model, when you have jobs in the system, maybe the service policy, there's not very many jobs, maybe it's not super efficient just yet, but the rule is that once you get up to n jobs in the system, you have to give out the full capacity of the system to the jobs once you have enough of them, once you've filled up the front with n jobs. So to be work conserving, if at least n jobs are present, the total service rate must be 1, the maximum. This might be a little different from the definition of work conserving you might have heard previously, because in those cases, people are defining it for a single server system. And so they'd say you need to hit your maximum service rate when you had 1 job. Well, we're defining it for finite skip systems, so you have to hit your service rate when you have n jobs present. So that's work conserving. So what's a WCFS policy? Well, it just means work conserving and finite skip. Okay, so let's just recap these policies that converge to the same mean response time behavior. We've got this picture, they're all coming here. And as it turns out, every single one of these policies is a work conserving finite skip policy. And we'll go through some examples in a moment. But there are many policies that don't converge to the same point and that aren't WCFS policies. So for instance, instead of prioritizing jobs first come first served in the MG1, we could have prioritized them shortest remaining processing time. And if you've taken Mark's class, you may know that this policy has the least possible mean response time. So it definitely converges to a different limit. If you haven't heard of it, don't worry, we're not going to be talking about it. We've got this unlimited processor sharing I talked about earlier. Well, that's not remotely finite skip. It serves every job in the system. It's not limited to n. Threshold parallelism with some different prioritization, or multi-server job, first come, first serve. We'll go through some examples in a moment. But the point here is this idea of work conserving finite skip, it nicely splits the policies that converge to this limit from the policies that don't converge to this limit. So that's encouraging. Okay, let's go through an example of a policy that may or may not be a work conserving finite skip policy. So here's the heterogeneous MGK. We've got 3 jobs in the system, and this one's being worked on with service rate 0.4, 0.3, 0.2, for a total of 90% of the service capacity is in use at this moment. So here's what I want to ask you guys. This is an audience participation talk. Is this a WCFS model? What do you guys think? Also, I'm just excited if you guys respond. Don't worry about having to get it right or anything.
I think so.
Yeah. So it turns out, yeah, this is a WCFS policy, and it's not giving out its whole system capacity just yet. That's because there's not enough jobs present. And once one more job shows up, now we're giving out the whole capacity of the system. And so, we've reached work conservation. And likewise, the rule of the heterogeneous MGK is that jobs go into the servers first come, first serve. So it is also a finite skip system. So yes, this is a WCFS model. Let's look at another example. So in this system, we got a multi-server job system. So that means every job tells you, I need 1 server, I need 2 servers, etc. And we'll just put them onto the servers first come, first serve. So maybe these 2 arrived the longest ago, so that's why they're in service now. So again, I'll ask you guys, what do you think? Is this a WCFS model?
This one I'm a little sketched out about. If one of the 1s leaves and you only have a 2 in the queue, you might not be able to use the full server even though there's a job waiting.
Yeah, exactly. So if a job completes, now we're not using one of the servers. And I mean, this isn't a situation of if there were more jobs that would fix that somehow. If more jobs arrived, they're still not going to fill the server. Doesn't matter how many jobs we have. So there's no limit n where we could possibly say you're work conserving, you're using all the servers once you reach that n. So in fact, this is not a WCFS model because it is not work conserving. Okay, so those are a couple of examples. Now let's do something a bit more exciting. So I told you I was going to define this ServerFilling policy for the multi-server job model. So now let me define it, and we'll see if we did succeed in making a WCFS policy for this model. Okay, so in the ServerFilling setting, we're going to focus on the case where the server requirements of each of the jobs are all powers of 2. So here we got some 1s and 2s and 4s. And we'll also focus on the case where the number of servers k is also a power of 2, 8. This can be generalized further, but we'll focus here for simplicity. So here's how the policy works, okay? We're going to find a minimal prefix, I'll call it m, which is a set of jobs that collectively require at least k servers. So we'll say, okay, we'll put this in the prefix, we'll put this in the prefix, we'll keep going until we get at least k servers. So that turns out to be this set of jobs. These 5 jobs collectively require 9 servers, and they're the minimal prefix that requires at least 8. Then our rule is, among this prefix m, we'll serve the jobs with the largest server requirement first. So ServerFilling will say, okay, you need 4 servers, you go into service. You need 2, you need 1, you need 1. Okay, we've hit 8 servers exactly. That's perfect. We filled every server, and of course they get service rates corresponding to the number of servers, proportional number of servers they use. So that's the ServerFilling policy. And so now, as always, we have this question: is this a WCFS policy? And this one's a bit harder, right? It's not easier to see at a glance whether it is or whether it isn't. Let me ask an easier question. Do you guys think this is a finite skip policy? Or is it not a finite skip policy? What do people think? I'm getting a nod from Jelani, so I'll take that as some participation. So yeah, basically, we're only going to ever serve jobs within this subset M. And how big could this subset ever be? Well, it's the minimal prefix that requires at least k servers. Every job requires at least 1 server. So the size of the subset M is at most k. So that k, that can be our finite skip parameter, our front size n. So great. But now let's look at work conservation. So it turns out, and we can prove this as a theorem in a paper, that server filling always fills all k servers. And the reason intuitively is because after you put every job into service, the number of remaining servers is a multiple of the requirement of that job. So when we had 8 servers total, we put a 4 into service, there were 4 remaining, and that's a multiple. And so as you keep going, you'll never be left with an annoying couple of servers left over that you can't fit a job into. And I'd love, yeah, I can go into more detail, but that's the intuition. As a server filling is in fact a WCFS model. And it's the first such model known for this multi-server job model. Okay, so I think you guys have a pretty firm understanding of what a WCFS model is. Now let me tell you a bit about how we prove our result. So we want to prove that the difference in mean response time with an MG1 is always between some pair of constants. And let me tell, and the key ideas behind this proof are based on this quantity of work in the system. So what is work? Work is the amount of uncompleted, we've got the remaining size of each job. Maybe it's partially completed, so we've got its remaining size, and we just add that up over all jobs. And so we're going to have 2 key steps that are both based on this quantity. And in particular, we're going to think of this quantity as a random variable and look at the stationary amount of work in the system. So the 2 key steps of our proof, first, that the mean response time in any WCFS policy pi is about the same as its mean amount of work in the system. And the second key idea is that the mean amount of work in the system is about the same as the mean amount of work in an MG1. So combining that with known results about mean response time in an MG1, we've completed our proof. So, okay. First, let me tell you about mean response time being about the same as mean work. So we've got our system, and we'll imagine that a special tag job, it's got a little star on it so you can tell it's special, but it's really not that special, which it's just some arbitrary job arriving at a random moment. It's a random job. It could be any job, but we're going to focus on this one. And so our question is, what's the response time of this starred job? Okay, well, we can break up this response time into a couple of pieces. First, it has to get through the queue. So we can look at its time in queue, and then it's going to have to get through the front. So one thing we can prove is that the jobs don't spend that much time in the front. That makes sense, right? Like the front is only n jobs. So on average, a job doesn't spend a huge amount of time in the front. Maybe one particular job might spend a long time, but it's bounded in expectation, and that's all we really care about. So we don't have to worry about time in the front. Now let's look at time in the queue. The maximum, well, here's what we can say, right? What's the longest a job could possibly spend sitting around in the queue? Well, it's got some amount of work ahead of it. And we know our system is going to be completing work at rate 1 because it's a work-conserving system, and we're in the queue, so there's lots of jobs for it to be working on. And so the maximum time we could possibly spend in the queue is the amount of work we see in the system at the moment we arrive, because the completion rate is 1. So if there's 1,000 seconds worth of work in the system when we arrive, by the time 1,000 seconds later, we better hit the front, because I don't know what the system's been doing that whole time, if not. So work-conserving systems, this amount of maximum time in the queue. We can flip that on its head. What's the minimum time we could spend in the queue? Well, you've got to wait for these jobs in front of us, except that maybe there's n or n-1 other jobs in the front that still have some work conserving at the time when we hit the front. So the minimum time we could possibly spend in the queue is the work we see on arrival minus n jobs. And based on the assumption I mentioned earlier about the job size distribution, we can prove that these two quantities differ by at most a constant in expectation. And so this roughly equal to sign here, that just means, differ by at most a constant. And one important fact is that work seen on arrival and time average work are actually the same distribution in the system, and that's because of a theorem called Posting. We saw arrivals, see time averages. So that's idea number one. Mean response time is about the same as mean work. Yeah, question from Z.
Hi, yeah. Sorry, maybe I missed or I've forgotten exactly what assumption you make on the job size distribution. Is it like bounded mean remaining size from any state or something?
So I didn't actually state the assumption, but it is bounded mean response, bounded expected remaining size from an arbitrary job state. So arbitrary age and arbitrary class. But the details aren't super important. Thank you. Yeah, any other questions about this first idea? Okay, so we're halfway there. Let's talk about idea number two. So we want to show mean work in the system is within a constant of mean work in an MG1. So to get some intuition, let's take a look where we've got the amount of work in the system on the vertical axis over time on the horizontal axis. So this might look like a picture like this. So these green jumps up here, that's when jobs are arriving. So work is suddenly increasing by some IID amount. And these blue segments are when, all the servers are full, or otherwise we're working at our full capacity. So work is decreasing, being completed at rate 1. And then finally, we've got these little red segments here where there's not enough jobs, and so work completes at some lower rate. And the key idea is, if we ignore the annoying little red segments here, this is identical to the behavior of an MG1. It's got the same size S jumps upward. It's got the same completion rate of 1 downward. It's just that these little annoying bits here are slightly different. But they only happen when there's not many jobs in the system, so maybe it's not too big a problem. So that's our intuition. Let's see how to make this formal into a proof. So to prove this, we're going to consider a quantity which is the square of the work in the system at a given point in time. And we're going to look at how that quantity changes over time. I say DDT, but really I'm including these discontinuous jumps as well. And the important thing is that the expected rate of change of this quantity in stationarity is 0. So what I mean is, if I set up my system in its steady state distribution, how much work there could be in the system generally distributed, the stochastic jumps upward of jobs arriving must be exactly canceled out by the decreases of work completed. We can use this fact to try to understand what mean work is. So these increases are jumps up according to this job size distribution, and they happen at rate lambda. So the expected rate of these increases is just lambda times the mean change in work squared when one of those arrivals happens. That's this difference. We can do a bit of rearranging, and we find that we get 2 rho times the mean job size plus lambda times the mean job size squared. So that's one side, that's the increases, and they're balanced out by decreases. And that's work completing at a certain rate, which I call B of T, how busy the system is. But that's just that total completion rate we looked at earlier. And the important thing is that rate is 1 if there are at least n jobs in the system. So what's the expected rate of decrease? Well, we can all take a derivative, and it's 2 times the mean of work times service rate. We can do a little math to rearrange this. It's twice the mean work minus twice the mean work times how much we're wasting, how much of the capacity of the system isn't being used. So we set these equal to each other, we do a bit of algebra, and we find that the mean work in the system is this quantity rho over 1 minus rho ES squared over 2ES, our old friend, plus a little error term. Mean work times 1 minus the busyness divided by 1 minus rho. And prior results, we already know that mean work in MG1 is just this quantity. So really, all we have to look at is this little leftover term over here. Okay, does this make sense, everybody? Any questions at this point? All right, some nods. Cool. So
I have a clarifying
Oh.
question.
that's good.
So W and B are not independent, right? They're both functions of what's in the system.
Exactly, right. And as we said, B really depends on if you got at least n jobs. Work certainly depends on how many jobs you have too, so they're very dependent with each other. Thanks. Okay, so sorry about the animations on this slide. So mean work we know is mean work in MG1 plus this extra term. Now, here's the important fact. If that B is less than 1, so if this term here is non-zero at all, then work is at most n jobs. And again, by that assumption I mentioned on the job size distribution, no one job contributes that much work. So we can bound mean work times 1 minus b as being some constant, at most some constant, the most work you could have in that case, times e of 1 minus b. And we know what this is. It turns out that the mean of the service rate is just rho. And so we can show that mean work is okay. There's a few typos on the slide. Mean work is at most mean work in an MG1 plus this constant c, the most work there could be with under n jobs. And we can likewise lower bound mean work as being the mean work of an MG1. And so taken together, mean work and mean work in MG1 are within a constant of each other. And so that completes the proof that mean response time is within a constant of mean response time in an MG1. All right, so any questions about this, this result overall?
I have another question then.
Mhm.
Okay, so this gets back to my question, to like mine and Anupam's asking about what are these constants? So
Yeah, sure.
So you said that the assumption you're making on the job size distribution is that no matter kind of what point you pause a job, there's some maximum remaining size.
Yeah, let me skip to my backup slide.
Okay, sorry. If you're so close to the conclusion, you can just keep going and we can talk
No,
about
no,
this
no,
after.
this is fine. So basically,
All
I
right.
made an assumption that no matter what age a job is at, on average, the amount of size it has remaining is at most this constant c. And so the bound I end up getting is basically just
Like n times c.
n times c, or to be really specific, n minus 1 times c is the bound on that work difference. And it turns out those CL and CH constants are both just n minus 1 times this constant c.
Plus and minus, presumably.
Exactly.
Okay, cool. Thank you. That was exactly what I was going to type into the chat if
Great.
I needed to ask. Okay, thanks.
Great. Okay, and thanks, Steve. Yeah, so we've completed the proof. Let me show you what this looks like in practice. So I said, we got these bounds, but let's actually look at this difference, mean response time under this policy pi minus mean response time in an MG1. And we'll compare that to load rho. Here I'm focusing on higher loads because that's where we're going to see the more interesting behavior. And at these loads, mean response time is like 10, 20, 30, 100, it gets pretty large. So it's pretty exciting that these two quantities are staying almost exactly the same. They really are bounded within a constant of each other. So in a heterogeneous MGK, it's a little over 0. In limited processor sharing, it's a little under. Threshold parallelism, it's up around 2. Multiserver job ServerFilling, it's a little less than that. In all these different policies, we're finding exactly what this theorem said, and even a stronger version of it, which is that these are really, really close to each other. And so the theorem is true in a very strong sense. So, okay, so it works in practice, it works in theory. Let's take a look at a few future questions we can work on. One question is, what if a policy was both work conserving and finite skip, but relative to some different job order? So all of this, we've defining finite skip and work conserving relative to first come, first serve ordering. But what if you took the same policy or the same model, but did it relative to some other ordering, like SRPT, serving the jobs of smallest remaining size first? What would your mean response time look like then? Another question is, what if you had a policy that was a model that was finite skip, but wasn't work conserving? So we saw that with that multi-server job first come, first serve. Do we make any progress in characterizing that sort of policy's mean response time? And finally, what if a policy sort of had some randomness involved in how it served jobs? And so it was finite skip and expectation, but not necessarily at every moment in time. So these are all interesting further directions that one could definitely work with. All right, so let me conclude. We found this unexpected similarity between a bunch of different queuing systems. They all converge to the same point as rho goes to 1. And to explain that similarity, we defined these work conserving finite skip models. And using that idea, we managed a tightly bound mean response time for all WCFS models, many of which there had never been an analysis for before. So that's everything I have to talk to you. Thank you all, and I'd be happy to take any questions. Thanks for the virtual applause.
So I have a question. In the job size distribution slide where you say C, isn't it at least expectation of the job size always?
Yeah, definitely that's a lower bound on it.
Yeah.
The whole point of this assumption is just to rule out more sort of really explosive job size distributions where this quantity might run off to infinity as age goes to infinity. So a Pareto distribution, for instance, we're ruling out here. But the results don't apply to those distributions.
Yeah.
Thanks. Yeah, any other questions?
So I have another question.
Yeah, please.
So you mentioned that empirically it seemed like way tighter than theoretically.
Yeah.
So can you say a few words about this? Like, for example, does this like end up not scaling in K for if you've got, as you increase the number of servers, or is there some, like, other than sort of just a single snapshot, is there any trend that's sort of different as something grows in which it seems tighter?
Yeah, so the part of the issue is this gets a little hard to simulate, especially when you try to throw a lot of servers at it.
Yeah.
But okay, so one way you can see in which it definitely has to scale with the number of servers is a lot of these policies, the mean response time when you have like one server will be scaling. Sorry, when you have very low load, maybe only one job in the system on average, will definitely be scaling with K. So in a normal like MGK or something, it would just be K times your mean job size. So
and this is because you're scaling the server speeds.
Exactly.
Okay.
So but as you can see here, like once we got near rho equals 1, that had gone away. So maybe there's some hope for a result like for rows near 1, the front size n doesn't matter, but I have no idea how one would go about proving that result, but it would be very exciting if one could.
Okay.
I have one question.
Yeah,
Does
please.
this work help you say anything more about each of these specific policies? Or is it just kind of you get this general result? Like, could you have guessed in your experimental results what each different WCFS policy might look like?
Yeah, well, okay, so one thing it definitely helped with is it helped us design the server filling policy. Because if
Mm.
we hadn't known to shoot for a work conserving finite skip policy, we maybe would never have come up with this. So that's one way it can help. In terms of, yeah, one thing we definitely looked at is making sort of specialized versions of the bounds for each individual policy. But mostly this is just in terms of saying that, like, well, if we use more of the properties of a heterogeneous MGK, more of the properties, whatever, we can say they're closer to 0. But it doesn't really necessarily like distinguish them from each other too easily. But for instance, I remember one could prove that this limited processor sharing, you get sort of asymmetric bounds where the upper bound is pretty close to 0 and the lower bound is like really negative. So that's definitely an example of what you can do if you start specializing to the specific properties of each of these individual policies. So definitely.
Got it. Thanks.
Absolutely. All right. Well, seeing maybe no further questions, so thank you all for coming to the talk.